Hello ladies and gentlemen, welcome back to what is going to be the fourth lecture for GGS300. So today we're going to be focusing on spatial descriptive statistics. Before we begin, I just want to say well done to those of you who've actually managed to get your assignments submitted. The marks will be released in due course once Amy's had a chance to actually take a look over them and grade them. The third assignment is going to be set this week, which is going to be on spatial descriptive statistics. So we're going to have the lab after this lecture, where we're going to go over some of these different processes, and then the actual homework will ask you to take a problem set and actually use some of the statistics in order to develop metrics and answer a set of questions. So just a reminder that I've posted on the actual Blackboard website just a very brief outline which kind of gives you a bit of an understanding for how to solve a coding problem. So I've had contact from a lot of you, that's great, but a lot of those problems have been like really quite basic coding issues that you're having, and therefore I just wanted to emphasize as a set of steps that you need to take really before you kind of reach out to me with a problem, and that's because solving coding problems is something which we all deal with on an hourly basis when we're writing code, but also I'm very cognizant that the point at which you learn and you kind of put two and two together and start to actually figure out how the code works is when you do have a problem, and then you kind of have to solve it. So this isn't me saying don't contact me, because I like hearing from you, and I think that really kind of helps you cement your understanding when I can reach out to you and help you when you're stuck. But the important point is you learn the most when you're going through that coding solving problem. So I want you to be able to learn how to do this. And, in this case, I'm giving you the labs, so you already have the code written. The reason why it's important to understand how to do this is that when you go off and you might have a different project, you might not have the type of code that I'm literally giving you. So you might have to write it from scratch, and therefore you need to know how to be able to piece together functions and pieces of analysis in order to achieve an objective. Okay. So there's three steps which I emphasize are: firstly, I want you to actually search for the error. So basically, if it spits out an error, then I need you to go to your chosen search engine, whatever that is, whether it's Google. Just copy and paste the error into the search engine and see what the answers show, because essentially pretty much every error that you're going to be getting, and a lot of them are very basic, the ones that you've been sending over, there's loads of answers which provide solutions for how to solve these, and your best bet is to look at Stack Overflow essentially. So if you go and you post a Stack Overflow question, that's your kind of second step. So maybe you haven't found on Google exactly what the issue is, but then by the time you realize that, well, maybe you could post your own question, then that's definitely a good option for you. So you'll need to look at how you post a reproducible example. So this is just a short little code snippet that says, this is the problem that I have, and this is the error that it's producing, and you might want to say what the output is that you ideally want. So take a look at the link that I sent there. Actually learning how to do that is an incredibly useful thing for you to do if you're going to go on and actually learn how to code in the future, either for your job or for further research. Then finally, if all of those things don't work, then reach out to me and say, hey, Ed, I've really been struggling with this problem. Please, can you help me? And the way that I want you to reach out to me is ideally give me a screenshot, because actually when I can see your code and I can see the error that it's producing, I can pretty much always work out the issue, or I kind of have a hunch as to what the issue is. If you just tell me I've got this error and I've got no idea what your code is doing, or I've got no idea what the error message actually is kind of specifically related to, then I'm not going to be able to help you, I'm afraid. So just try and follow these steps, and I think it will become a lot easier for us then to kind of progress in terms of getting the assignment submitted. Okay, great. Let me know if you've got any further queries about how the course is progressing, or if you want to reach out for any particular reason. You know where I am, you can hit me up. Course update, I'll be setting several tests in order to basically just round off the descriptive statistics part of the course. So that's the first third, if you remember, if you go back to the syllabus. Do watch for announcements for this. It's going to be in the kind of latter part of February. So I think we're scheduled to have the final the final session on descriptive statistics, which I think may be probability, which is around the 22nd of February. So it's going to be around then that I start to update those tests, send them out to you. You need to complete them. They basically prepare you for what will be the first midterm exam that we're going to have, which will obviously be graded. Okay, great. No, we're not doing that. Presentation objective today. So today I'm going to be focusing on spatial descriptive statistics. We're going to be going over a variety of metrics and methods, and then the techniques for how you use those. And it's kind of going to be mirroring the content that we learned in the previous week, which was basically spatial descriptive statistics. So there was no space necessarily brought into those descriptive statistics we used in the previous class, whereas today I start to show you the kind of analogous functions that can be used in order to apply them in spatial contexts for whatever spatial processing you may desire. Concepts. Okay, so what are descriptive spatial statistics? Well, previously we focused on central tendency, so metrics of particular distributions, measures of dispersion, so how dispersed, how spread out, how much variation there is in specific data sets, and then measures of shape. So are there what's the symmetry within a set of data? What's the kind of, do we have quantitative measures which basically help us understand different aspects of the shape of the distribution, which obviously we do, and we covered that. Okay, so spatial scientists do very similar things with descriptive spatial statistics, and you might have heard people refer to this as geostatistics, for example. So it's just applying those statistical methods to some sort of analysis of locational data. So I mentioned before that last week we covered non-spatial. This week we're covering spatial. Essentially, there are kind of comparative techniques, but not all of them are actually useful. And that's because actually when we think about spatially displaying data, well, we don't really need to very often use the same kind of distributional measures if we can just visualize the data in some sort of 2D, 3D, or 4-dimensional map, okay? So it's not always necessary for it to have kind of direct complements to those techniques in the spatial setting. The point of actually using some spatial techniques is that we can put it into that more realistic spatial landscape for however many dimensions you want to use. So just in case you're not familiar with all of those dimensions, obviously 2D is an X and Y coordinate like you would have on a graph. 3-dimensional could be maybe you've got a 3D model, so maybe you've got altitude in your map, and that's providing some sort of 3-dimensional perspective. So for example, if you go into Google Maps and then you've got the 3-dimensional view, and they've got some pretty cool modeling there where they're actually able to kind of give you an understanding of both the landscape topology, but also buildings and trees and that kind of 3-dimensional insight. And then 4th dimension is just the same as 3 dimensions, but you add in the time dimension, okay? So you can look at some of the work that I've done on 4-dimensional modeling, which is basically just 3D over time. So it's less complicated than it sounds. Okay, we have all these different methods, and generally I'm focusing here on point geometry, okay? So if we look at the non-spatial measures that we used last week for central tendency, we used the mean. For dispersion, absolute dispersion, we used the standard deviation, and the relative dispersion, we used the coefficient of variation. So remember that the absolute dispersion refers to dispersion in the original units. Relative dispersion refers to a standardized measure for us to understand dispersion. So for example, in the standard deviation, we could be measuring in meters, but in the coefficient of variation, we could be measuring in percentage points, okay? And that allows us to compare between different data sets, which maybe aren't in the same unit. Then on the spatial front, well, for central tendency, we're going to cover now these different techniques, so the mean center, the median center, the Euclidean median. And then also we have, for the absolute dispersion, the standard distance. That's fairly straightforward. It's very much like the standard deviation we'll be covering, except we're focusing specifically on the distance covered. however we decide to measure distance. And then for the relative dispersion, we'll be focusing in this case on the relative distance, which we do in the very final part of the lecture today. Okay. So descriptive statistics are used to conduct a wide variety of assessments for spatially explicit data. So just imagine that these are point patterns. They've got X and Y coordinates. So we're able to explicitly locate those points within space. And then we're able to understand the degree of variability among those different points for whichever measure we decide to use. So the requirements obviously there are that we've got coordinate-based data. That data will end up having some sort of a coordinate reference system. So whether that's UTM, a state plane, lat longs, a WGS84, whether these are projected or unprojected. So unprojected, probably often in degrees measured, like lat long, but you can have projected coordinate reference systems, which basically is just using an explicit distance, for example, such as meters. And that's obviously an important catch if you want to measure distance, to make sure you've got the right units in your coordinate reference system. Otherwise, you'll introduce mistakes into your work. And the fact also that this kind of needs to be point-based data as the requirements which we're using here. So that could be anything. So I'm going to use an example of warehouses in some of the metrics that I'm going to give you here today. So let's just say that they are warehouses for your distribution business, and you're in LA and you've got a lot of distribution warehouses. You've got like 20 across the city, and maybe you want to understand something about how you organize your stock across those 20 different distribution centers. Generally, this is focusing on points. Fine line strings, so lines or polygons, so actual physical shapes are kind of more advanced. There are metrics for those, but I mean, an easy way to just actually reduce the dimensionality of that data down is you can reduce lines down into single points if you just want to take the middle point across that line for each one, or polygons, you could find the centroid or the representative point for that polygon and just reduce it down to a point. I mean, I do that all the time if I don't want to bother with the computational hassle of crunching through polygons, which are more complicated, there's far more data points. You can just take the representative point, and that's good enough. Okay, great. Well, let's move on then. There's not too much that I want to say here. How do we actually calculate these geostatistics? So you could just do these manually if you just want to do it in Excel. If you knew the function, fine, we could do that. It's not particularly straightforward and easy to do that. I mean, you can need to know how to translate the math. So, I mean, it's nice if you kind of want to show, as I did in the previous lectures, exactly how to do something. But these aren't kind of explicitly spatial. I mean, generally, I wouldn't recommend really doing too much in these, at least not the proper analysis. Geographic information system software. Okay, so yes, there's lots of spatial functionality within these. So you'll be familiar probably with ArcMap, ArcGIS, so the Esri-based software, which is quite commonly used, which you should, I think you have the ability to access. Great, okay, so that's got a whole load of built-in functionality. I don't actually use ArcMap, so we will be using it in this class, but I use Quantum GIS just because it's open source. I mean, it basically does exactly the same as ArcGIS, but I don't ever have to worry about getting a license for it. And generally with what I do, I kind of write most of the processing in code, and then actually I just check that the analysis has been done correctly to those shapes or points by opening it in either ArcMap, for example, or QGIS. So that's kind of a more advanced way that you might start to use the software that we've been discussing here. But I mean, we'll do some of that in the lab today. There's lots of geostatistical techniques that you can use within ArcMap or QGIS. And then I did mention before that you could advance to kind of more kind of proficient approaches using programming and software. R allows you obviously to do both spatial, non-spatial data sets, and actually a lot of my maps I create in R because then I can just run the code even if the data changes and it just spits out the map for me once I've generated it, so that's kind of nice. but also Python's getting a lot better these days in order to do both the geostatistics part, but also to be able to do the mapping part if you want to. Okay, so today in the lab what we're going to do is use R for some of the hand calculations, and then we're going to use ArcMap for the visual analysis, but I'm also open to using QGIS if you want to. So let's move on now onto the spatial measures of tendency. The central feature is basically out of a set of points, you're trying to find that point which has the shortest total distance to all of the features in the data set. Okay, so imagine that we're working with point data. The central feature, therefore, is going to be the central point. And the calculation procedure for this is that you basically need to find the distance from every single feature to every other feature individually. And then you need to sum all of those distances, and the one with the minimum distance basically is the central point, central feature in this case. So it's very, very easy. It's not complicated at all. We just need to be aware of how we calculate distance. So I'm going to give you an example of how we do this. I'm going to use my beautiful black Labrador George. So usually you can find me walking in the countryside with him. Here he is on one of our favourite walks in summertime, which given how cold it is at the moment, I'm very much looking forward to. And you know, pretty much every morning I'll take George out down to the park and he'll run around and meet all the other dogs. Okay, so just imagine in this particular example, I put a GPS trace tracker on him, and I'm going to go let him kind of run around and do his thing. He's going to go see all the other dogs. He's going to create this huge GPS trajectory trace, okay? And this is basically all the places that he ran over like a 5-minute period. And just imagine then, I take the data from that, and then every 30 seconds I record a point, and each one of those points is going to be, you know, let's just say it's a lat-long coordinate or whatever. It's going to be an XY coordinate that then we use to calculate the central feature, okay? So this is how we actually got our set of points that we're going to analyze here. The question is, which is the central point? How do we do that? Well, essentially, we need to go through that process I mentioned before. We need to build the distance matrix, and then we need to sum all of those distances, and then we need to find the minimum one in order to find the right point. So that literally means for every single point in the data set, you need to measure the distance to every single other point, okay? And let's just say that's how you generate the matrix for doing that. So a matrix in this case, if you're not aware, is let's just say we've got the ID for each one of those points along the x-axis and the y-axis, and then basically you're able to find the distance between each point to every other point across that dimensional plane based on this type of approach. The question is, well, how do we measure the distance? And therefore I need to give you some background as to how we do that. It's quite common to use the straight line distance, the Euclidean distance, also called the Pythagorean distance. So essentially what we're doing here is, if you, for example, have two sets of points, maybe you've got xi, y here, which is point I, and xj, yj here, which is point j. Essentially what we're going to do is we're going to find the distance on the x-axis and the distance on the y-axis between these 2 points. That gives us A and B, and then thankfully, due to Pythagoras' theorem, we're then able to basically find the distance between those 2 points, square them, add them together, and then take the square root, and that's how we find the hypotenuse here, so dij, so the distance between these 2 points. And obviously that's based on the right angle triangle, allowing us to basically find the hypotenuse in this particular way. Okay, so I mean, I'm sure you must have covered Pythagoras previously, you know, I've just posted at the bottom here that funny video that went viral on TikTok a while ago of the kind of 16-year-old girl basically saying that she doesn't believe in math. And obviously she got kind of lambasted for the things that she said, but she also raised some kind of important questions, which is like, how did you actually work out that this type of relationship existed? You know, if you're actually building the types of buildings that were really quite advanced architecturally, you know, 2,000, 3,000 years ago, then actually this is how you came to that type of problem, is you needed to work out how to actually measure certain parts of the roof, and that's how these types of math-based theorems ended up being developed, because you're able to work out how to develop a sloped roof based off certain geometrical lengths. Okay, so I've just posted the link down there. She also raises some important questions about kind of scientific philosophy. Okay, so are we actually discovering quantitative relationships which are within the data that exist in reality, or are we just finding mathematical relationships that apply to a process nicely, but which we therefore are just kind of imprinting on the world based on our own perspective? No, I'm not going to get too much into this. I just thought it was quite funny that something like this would, number one, go viral, and number two, raise such interesting questions. But I'll just leave it there for you in case you're interested in just taking a look. Okay, so that's basically how we get the distance. You could do it in multiple other ways. Okay, so here, I'm saying it's the straight line distance. It's as the crow flies, for example. It's not taking into account things like the curvature of the Earth, so the great circle distance, for example. There are other types of distance that we may consider for actually calculating a particular route. So for example, here we've calculated the Manhattan distance, which is just an example from the book. So I actually did this flight about a year ago this week. So I had to go from Dallas, Texas to Ohio State, which is in Columbus, Ohio. And actually the way to do that is to fly Dallas to Chicago, Chicago to Columbus. So I thought it was quite cool that it was in here. So I've just used it as one example of Manhattan distance. So when you think of the Manhattan grid, basically when we say Manhattan distance, what we're saying is that you can't travel along the hypotenuse, which would be the straight line distance, which we covered before. So you see it's called the Euclidean distance here. So therefore what we have to do, because it's on a Manhattan grid, is we have to go down, in this case, if we're going Chicago to Ohio, Columbus, Ohio, then we have to go down the y-axis and then across the x-axis, and that's the distance that we end up getting. Okay, so that's how we basically end up with, in this case, the Manhattan distance. The network distance is just basically the travel distance that it takes to get through the network path. So the best example of this is when you tap in your location that you want to go to in Google Maps, and then it basically very quickly runs through all of those calculations. So it's actually based on what's called Dijkstra's algorithm, and then it finds the shortest path along the available road network or paths that you have, and then it finds a travel route for you to take. That's basically the network distance. Okay, so you're traveling through the road network, and I've got examples in papers where I've used this. So it's quite nice to route things along roads, because that's generally how it's going to take place. For example, if you're going to plan an electricity network in rural Peru, you're probably going to put most of your electricity assets along the roads because it's easy to actually access. So you can therefore plan how many meters or kilometers of electricity line you're probably going to need along that road network. And obviously the road, if you're in the Andes, then it's not going to be a straight road. So basically it gives you quite a nice indicator, if you do it that way, of how you probably will need to plan the network and what the cost may be. Great, so what we've done here, essentially just to recap, is we've spoken about getting the central feature, we've spoken about measuring the distance, and I've gone over the straight line distance, the Euclidean distance, the Pythagorean distance, how we calculate that. And then I've just mentioned very quickly other types of distance that we may have, such as the Manhattan distance, which is basically on a grid system, or the network distance, which is the type of distance that you would have when you're actually on your phone and you're using whichever your preferred mapping app actually is in order to navigate somewhere. So there's an example of how you calculate the central point within the book. If you go to page 73 within the chapter which you need to read this week, which is part 2, chapter 4 on descriptive spatial statistics. And there it's just providing you an example of how you actually get the distance matrix. Okay. Now, I just want to give you a brief kind of real world example of how you would use this, because, what I really struggled with when I was learning math, particularly when I was at school, was I felt like there wasn't enough application of the techniques that we were learning. And actually now what I find really useful is when I'm learning something new, I kind of think, well, how's that implemented? Okay, you're sat in Google, you're developing an app, like where is the math that you're learning actually implemented within the software that we use on a daily basis? And when I do that, it's much easier to kind of understand how something's applied. You kind of see the beauty in the math, the theoretical part, and then you kind of see the use of actually applying that into an actual application. And I think that that's so much more powerful than me just standing here and saying, these are the formulae, and you kind of nodding off or browsing Instagram or whatever else you want to do when you're bored of listening to me. So the point is that I just want to give you an example here of, well, what would the real world application be for the central feature? In essence, imagine that you're that distribution warehouse owner in LA that I mentioned before, and therefore you need to kind of distribute your products to all of the warehouses that you've got across the city. Obviously, you might not want to have a central hub because you might have, a 2-hour travel time from one side of the city to the other, particularly if it's rush hour. So therefore, you want to be aware of all the different hubs that you have across the city. And what you may want to do is to minimize the distance between all of the different hubs that you have, and use the one hub that basically you're going to find as the solution as basically being the central hub. Okay, so that's where maybe you put your headquarters, that's where you put your office functions, so that as drivers or other people come in to collect gear from that place, they're able to discuss or pick up paperwork that may be relevant for stock management and things like this. So this is kind of a good example of how you would actually apply this. You'd want to minimize the distance to all the other warehouses, essentially. Okay, great. So I hope that that provides you with a little bit of an example of why we do this. There's these other measures which are slightly different. So now we're going to focus on the mean central point, which is just the average location across a data set of points in this case. So think of it as very much analogous to the arithmetic mean that we covered last week. So it's basically the summation. The arithmetic mean was the summation of all of the values divided by the number of values that we have. But in this case, just imagine it as kind of like the center of gravity of all of those points that you've got within your data set, okay? It's widely understood, widely used. The calculation procedure is very simple. In the same way we did for the arithmetic mean, in this case what we do is we just sum all of the Cartesian values. So basically what we mean by that is we sum the x coordinates and we sum the y coordinates separately. Okay, and then what we do is we divide by the number of data points that we have, and that gives us our average x coordinate and our average y coordinate. And when we put them together, that's our average point in the data set. Okay, very simple. I'll be able to show you how we do that later in the lab. Imagine we go back to the example in the park again. So, it's 7:30 a.m. on a Thursday, and I've got to teach GGS300 that day, and I take George down to the park before work starts, and he's running around, he's seeing all the other dogs, okay, and he's got his GPS tracker on, and then I just take those 30-second interval locations, which provides me with a set of data points. My question now is, well, where's the mean center out of all of these points, okay? When you actually calculate that, the difference between the mean center here and the central point that we had before is that this time the mean center, which is basically the center of gravity of all of these points, it doesn't necessarily land on a point, okay? So it doesn't even have to land within all of the shapes, in fact. But you need to kind of be aware that this is a differentiating factor from the previous process that we carried out. Okay, so it's quite easy to find that mean center, as I described before. It's written in the book. It's really quite simple in this case. So to find the x bar coordinate, so the mean x coordinate, we just need to sum all of the xi coordinates and divide by the number of points in the data set. And then we just need to do the same in order to find the y bar coordinate. So it's summing all of the yi coordinates and dividing by the number of points in the data set. And that's basically how we get the x bar and the y bar, which is the mean center. So you can look that up on page 63, 64. provides you with some basic examples of how you calculate that in a table, also describing that within a figure. And as I mentioned before, that point doesn't always land within the area's shape. Okay, so I've just given you an example here. Find me the center of gravity for Maryland as just one example, and actually you might end up with a central point which is outside of the actual shape. So let's just say we divided Maryland up into 1 by 1 kilometer squares, and then we said find me that mean location, the mean center, and maybe this is the type of point that it would produce. Okay, so you just kind of need to be aware of this in case of you producing an estimate which lies outside the area that you might be working with. And a good example actually is I use this all the time, and what you don't want to do is to plan to put a new node for an infrastructure network in the middle of a body of water, which is the type of problem that you will encounter if you do this. Okay, so fortunately in this case this point is probably in North Virginia. But in the other work that I've been doing, particularly in parts of Africa, when I'm planning infrastructure networks over really large areas, quite often I find, if I'm not careful, that point, if you find the weighted center of a government region, you might put it in the center of a lake, for example. So you just need to be careful with that. So it's partly also because it's affected by the number of outliers as well. So we did cover this within the previous work. Can you remember in last week I mentioned why we would use the median income as opposed to just the average income for a distribution of household incomes, perhaps either across the US or just across Virginia states? And that's obviously because the likes of, the Elon Musks of the world, the Jeff Bezoses of the world, the Bill Gates will just skew the whole distribution so that your average income actually looks far higher than it really is. Whereas if you use the median, then basically you're getting the middle point, right? So that's kind of why we like to use the median over the mean, for example. Okay. So let's just provide a little bit of an example of the geographic center. So if we go in the book and we look at figure 4.5, this is just providing you with pretty much a decadal level of insight for the geographic center of the US over time. So 1790, something like 14 years after the Declaration of Independence, most of the population of the US, for example, is heavily weighted in that New England area. The population really hasn't started to move westward. Over time, obviously, that population starts to spread over what at that time was obviously Native American land. Starts to move out westward over particularly the 19th century. And then I think one of the interesting things is, you see a big shift between 1940, 1950, 1960, and that's because essentially a lot of the essentially male soldiers that were recruited, particularly from the main agglomerations in New England, so New York, for example, Boston, sent to the Pacific War, so essentially down to the Pacific coast. They were taken overland down to places like LA, San Diego, from where the Navy was sailing at that time to go out to war. And essentially they realized that California was an incredibly nice place to live, higher standard of life than perhaps if you were in central Manhattan or Queens at the time. Basically a lot of people ended up staying. And that's really when California particularly had a huge growth spurt from the 1950s, 1960s, with a lot of those service members basically deciding to put down roots in Los Angeles, San Diego, also the Bay Area. So that's when the West Coast really started to develop at a much stronger rate in the 20th century. So this just gives you a little bit of an example of how you can look at the geographic center of weight over time based on, in this case, on the census information. So the weighted mean center, we covered the weighted mean in the previous class. So for example, we were considering what the implications of getting the annual temperature would be if, for example, we have different numbers of days within a month, right? So we wanted to take this into account in order to get a more true, a more accurate representation of what the annual mean temperature may be. In this case, we can do the same. Maybe we want to weight our coordinates based on some sort of counting parameter. So maybe it's the population, so it could be a city size, for example. That's pretty common. I think I did mention gravity models in the first lecture when I was talking about the influence of Newton, how Newton's theories around the Enlightenment helped us understand gravity in terms of the size of an object, the force of an object in relation to its distance, and that actually a lot of these models are still used today as very good ways for understanding trade and migration, for example. We could also consider income, we could consider crimes, cost, magnitude of event, but really it's quite simple to calculate. We basically just want to find the weighted mean center, and then what we're going to do is for each of the individual points that we have when we want to take the coordinate, and then we want to take the weighting factor, so the frequency or the weight of the point, and then we want to multiply them together to get the numerator, and we want to divide by the sum of the frequency for the denominator, and that gives us either the weighted mean for the x coordinate or the weighted mean for the y coordinate. Okay. And the weighted mean can be used to calculate things like the economic center of gravity. So if we go back to 1 AD, essentially the economic center of gravity for the whole world at that point is somewhere on the western border of Pakistan, so modern-day Pakistan and Afghanistan, so the Khyber Pakhtunkhwa region. And essentially it actually diverged a very small amount over that kind of 1,000, 1,500 year period. So this is kind of the old Silk Route road. And there wasn't that much development at that time, and it was really when the Industrial Revolution started kicking off, which was in the late 17th, late 18th century actually, when steam power started to begin. And actually that's when predominantly European countries, so mainly Britain, Germany and France, started to develop at quite a rapid rate. And that basically pushed forward for about 100 years until, so essentially by about 1913 that you've got there, you can see this big shift westwards. And that was really when the US started to emerge as the largest economy in the world. And that was basically fully cemented by 1940 and then through the 1950s. And then essentially as you start to get to 1960, there starts to be development in other parts of the world, particularly the US and parts of Europe start to go through deindustrialization processes. So a lot of manufacturing started to move to other places through the 70s and the 80s and the 90s. And then that's kind of only been compounded even more over the last couple of decades. And that will continue to do so, particularly over the next century, as essentially a lot of those Asian nations really start to economically develop over the next couple of decades. So you can see things are starting to move eastwards again. Okay, so that just gives you a little bit of example of how you may want to use the Earth's economic center of gravity. So here it's taking into account, for example, the coordinates and also the amount of gross domestic product, so the economic output of all the countries in the world. That's how they produce this particular time period plot. Okay, we can get the median center as well. So essentially this is the location that minimizes the sum of the unsquared distances. It's somewhat more tricky than the other metrics that we were able to basically just produce by taking the distance matrix in many cases. So in this case, it's a repetitive process that narrows down to the right solution. So this is what you might call iterative. So it needs to kind of loop over all of the different potential options that it has and record the values that were produced, and therefore I'm kind of describing this as more like a brute force optimization problem. So when I say brute force, it's just using computing power to crunch through lots of different iterations of calculations, and then once you've decided to finish your computation period, you just pick the value that has in this case, the minimum distance. I'm not sure we're going to be covering this in too much detail, but I just wanted to make you aware that this is one way that we could try to estimate the median center. And here's just another brief example of how the median centre for the population of the US between 1880 and 2010 could have been estimated. So you'll notice that the fact that it's in Ohio and Indiana, it's quite substantially different from the mean centre that we calculated quite a few slides back now. And I think also there's an important definition here that the census uses, so it's kind of different for how you end up calculating it as well. Okay, great. And another metric that we could use, and I'm going to return back to my favourite example of hurricanes in order for us to actually get the linear directional mean, but imagine that you had a set of line strings, so a set of lines, and that those lines have a direction on them. Essentially, we want to find the overall trend for multiple lines, okay? So the resulting value for the linear directional mean will be the angle of the mean vector that we produce, okay? So let's just say we have all of these directional arrows over here, so directional line strings, whatever you want to call them. And then we're able to produce a single mean estimate that gives us the LDM summary, the linear directional mean. And the way that we do that is basically we need to take the theta I, which is the key input, so it represents the direction of the set it's the direction for each linear feature basically. And we need to sum up the number of lines that we have, and then we need to basically use that with the sin sign and with the theta I as the numerator, and then the sum of the number of points cos and theta I for the denominator, and take the arctan, and that's how we produce the linear directional mean. So that's basically the math for how we do it. Don't worry about it. We're going to actually calculate it within, I think it's within ArcMap, I'm going to do it. So the essence of this is that you don't need to know the formula explicitly. We'll use a piece of GIS software in order to calculate this, but you just need to be aware of kind of what it's doing under the hood. And here we go. So imagine that we have hurricanes or tropical storms that cross Puerto Rico. So obviously, these parts of the Caribbean are extremely nice places to live for 11 months of the year, and then when hurricane season hits, it is a worrying few weeks. So one of the things that you want to be able to do is basically to predict the path of different weather patterns, for example, like a hurricane, and you want to provide some sort of prediction in order to do that, so that basically, if it's heading on through Puerto Rico, you can provide some advance warning as to when it's going to hit. If, for example, if it's then heading on up the eastern seaboard and it's likely to make landfall in Florida, then ideally you want to give people who live in Miami, for example, more time to try to move up the state of Florida, and ideally into parts of Georgia, so that they're away from that kind of storm surge area. So ideally this is quite a nice technique in order for you to make an estimate as to the potential hurricane route. And I think I used in a previous example the fact that most of these big weather models these days that are being used to estimate weather patterns are actually ensemble models. So they run the model thousands or tens of thousands or millions of times on huge supercomputers, and then they basically try to find the mean path, the most likely probable path that weather pattern is likely to take. And actually it's kind of quite similar to what we're doing here basically. So we end up taking the linear directional mean, although I'm not sure if this is a specific metric that they use when they do those computations, but this kind of provides you with a similar sort of understanding that there's lots of different potential paths that it could take, and we want to find the most likely, and this is one way to do it. Okay, so let's move now on to spatial measures of dispersion. So we can calculate the standard distance. So this is analogous to the standard deviation. The standard deviation is just the average amount that the data moves around the mean value, okay? And it's an absolute metric, so that means it's measured in the underlying units. So if we're interested in meters, and that's what the data set is measured in, then the standard distance will be measured in meters as well. Okay, there's two different formulae that we could use here to get the standard distance. So essentially we're taking the sum of the squared deviations for the x coordinate, the sum of the squared deviations for the y coordinate, and we're adding them together to get the sum, and then we're dividing by the number of data points that we have, and then we're taking the square root. Okay. So let's return back to our classic example of George running around the park, wanting to see everyone like a happy Labrador that he is. So we've got that set of points that we're interested in. This has a much higher standard distance. For example, if there's lots of people in the park, he's running around a larger area, it's got a larger distance between all the points on average around the mean than this example here. Maybe there's no one else around, he kind of stays around me, he doesn't really move much, and then we have this point pattern that's less dispersed, and then therefore in this particular case the standard distance would be lower. We can also weight the standard distance, so it's kind of quite similar to the weighted mean center that we used previously. So what we want to do is we want to take the summation of the Fi, so that's the weight variable over here, and then we want to use that as a way to actually weight the distance that might be traveled. So for example, imagine that we go back to our warehouse example, and we want to actually include the amount of available floor space in the calculation as a weight. So maybe some of our warehouses are in a great location, but they don't have enough floor space for us to make it the hub, the HQ, the headquarters, and as a consequence we want to be able to include this within our analysis, and therefore we're able to actually include a weight within that standard distance measure, for example. We can also take the standard deviational ellipse, so it's another spatial processing technique, this time focused on actually developing an ellipse pattern. So it takes the orientation of the particular points into account with the standard distance. So the way that we actually do this, and we'll do this within ArcMap, is to calculate the standard distance separately for all xy coordinates, and then we create a cross of dispersion, which I'll show you very shortly, which is basically just drawing lines of the standard distance for x and y from the mean center parallel to the x and y axis respectively, and then we cross rotate this based on a trigonometric function to minimize the distance across all of those arms. Okay, so you can see the math at the bottom here that we use to calculate the standard distance as the first point. So you'll recognize that for each of those x and y coordinates, we're basically taking the sum of the square deviations, dividing again by the number of data points that we've got in the sample, n, and then we're taking the square root to get back into the original units. That basically produces this here. So you can see the standard deviation, so the standard distance for x and the standard distance for y here around the mean center, and then we're able to get the cross of dispersion and actually use an angle rotation. And the point of this is that we're able to, for a set of points, maybe compare different time periods. So this is just one example here of so this is anti-shipping activity off the East African coastline between two different periods. I mean, this is basically piracy, and Somalia is very well known for having these very technologically capable pirates who try to board all of the major tankers and shipping container vessels that go up the east coast of Africa, or come across the Indian Ocean in order to try to go up the Suez Canal. And essentially what these points show here, using this standard deviational ellipse approach, is that in 2009 we had our points all kind of clustered around this center here, and in 2010 we have this much larger ellipse. And actually this is because technologies evolved over this year, between these two periods. So the pirates basically got much faster ships, much more advanced ships, and they're able to basically go further distances. So all of those interactions that are taking place with pirates basically trying to board vessels take place at a much larger distance now, and when you use these two different metrics, you're able to kind of nicely see how these different interactions have spread out. Interestingly enough, there's actually a really cool startup company based in DC, not far from GMU, which I just love. And they're basically using satellites that they've launched in order to track ships, particularly ships that might have turned off their communications but still have their radar on. And they're actually using the satellites to pinpoint those ships that are basically trying not to be seen. And actually the DoD and other parts of the Pentagon, they're focusing on anti-piracy in this part of the Indian Ocean. Essentially are using this tech in order to try and identify where these boats may be and give vessels a warning that there might be a particular ship heading towards them, essentially. Okay, great. So that just gives you an example of how we might use that particular approach. So we might be interested in the relative dispersion. So remember, the absolute dispersion is measured in the original units. The relative dispersion is a metric like, for example, like a percentage that provides, it's kind of agnostic of the units of measurement and more providing you some sort of overall understanding of the dispersion of the data. So in the standard deviation in the classical statistics we did last week, that would be measured in the underlying data values. The coefficient of variation is basically a way for us to understand the kind of percentage variation, for example, between two different data sets. So the standard deviation can be used if you have two different data sets and they're measured in the same units, such as meters. Maybe the coefficient of variation, we're using different metrics and it's not that easy to convert between them. And therefore, we use the coefficient of variation to say, well, this one data set has 20% variability and this other data set has 50% variability. So regardless of the units, I know where there's more dispersion taking place. Okay, so that was just a bit of background for what we did last week. The issue is that in geostats, there's basically no spatial equivalent to the coefficient of variation, and that's really because essentially when we change the coordinates reference system, the mean center changes, but the standard distance does not. Okay, so there's good examples over here on the right-hand side. You can see the mean center and the location of these points based on this coordinate reference system for X and Y. If you then look at the bottom case, case 2, obviously the coordinate reference system has changed. They're completely different coordinates, but actually the mean center's distance different. But then if you look at the standard distance, it's 1.54 in both of these cases, okay? So this just gives you a little bit of a flavor of why you know, this may not be that useful in this case, because kind of space is slightly different when we flip between different coordinate reference systems. So what we often might do is we might add an area or a region in order to understand dispersion, right? So we might draw a boundary around the outside, and we kind of covered this in previous examples, you know, some of the issues with boundaries, for example, the spatial modifiable areal unit problem. In this case, just imagine that we've drawn these boundaries around the outside, but then they might end up giving us different potential results. So in case 1 here, the actual standard distance between the points might stay the same across each of one of these boundary areas. So it's the same absolute dispersion, but actually the relative dispersion across these different areas is actually decreasing, right? Because here the points are kind of evenly dispersed. In the middle, we've got a larger area now, and the points are kind of clustered in the middle. And in the final one, we've got a much larger area, and the points are nowhere near the perimeter. And if we took that into account in our relative measure, then we would end up getting different results, even though the absolute measures stayed constant. The same can happen as well in case 2, where, for example, we have the same relative dispersion. Okay, so the dispersion of the points within the boundary is pretty much the same. The difference is that you've actually got different in the absolute dispersion. So the standard distance here is going to be different between these two sets of points, even though the actual level of relative dispersion between them hasn't changed at all. Okay. So these just give you a little bit of an example of the types of problems that we might come up with when we're focusing on dispersion issues, and we're interested in the relative dispersion versus the absolute dispersion. So finally, just to finish off this lecture, we are able to take the relative distance. So we can use this as a measure of spatial dispersion based on the point pattern standard distance and then the size of the study region which we define. So for example, the denominator in this case is going to be the radius of a circle, so RA down here is the radius, with the numerator being the standard distance. And essentially that's how we calculate the relative distance between these two here. Okay, it allows direct comparisons of point patterns in different sized regions. And the way that we can do that, so we should have the standard distance already. We just need to then find the radius. So for example, we can do it to find the area of region A. We can solve the area for the radius using our standard equation. The area is equal to pi r squared. So if DC is 68.3 square miles, then we can approximate that the radius of that area is 4.7 miles. So then we can use that within our metric in order to calculate the relative distance of a set of points that's distributed across the DC city region. Okay, well, that's the fourth lecture. I hope that the content that we covered today was fun. I hope that it was interesting for you, and obviously this is the kind of high-level, more theoretical part of the materials for this week, and then in the next session we're going to focus on both a bit of lab work in R and then also a separate video where we do some work in ArcMap. And that kind of sets you up in order to produce any work that might need to be submitted for the next assignment, which is due, well, it will be due a week from the day at which this work goes live, essentially. So watch on the Blackboard. Whenever I set the assignment, I always set the due date in the title, so you guys should have a very clear understanding of when it's specifically due. Okay, great. Well, thanks for tuning in again, ladies and gentlemen. It's been really nice to see you, and please let me know if you've got any further queries and questions. Otherwise, have a great week. Thank you.